Good morning, everyone. My name is Nihat, and today I am excited to present our project, AI-powered origami recognition and instruction system. In this project, we aim to bridge the ancient art of paper folding with modern computer vision. Developed here at the Holland Institute of Technology, our goal was to create an end-to-end pipeline that can classify complex geometric shapes using deep learning. Now let's dive into the core of our project. We have built an AI-powered system designed to recognize any origami model from a single photograph. We like to call it the Shazam for origami. Just as Shazam identifies audio patterns, our system analyzes geometric features and folding patterns using computer vision. The project stands on three pillars: AI recognition, advanced neural networks for precise classification, computer vision, allowing the system to see and interpret complex paper edges, deep learning, training on massive datasets to distinguish between similar models like a crane and a dragon. But we go beyond recognition. Our final goal is to provide instant step-by-step instructions, making the art of origami accessible to everyone, regardless of their skill level. Now let's look at the technical architecture. We didn't just build a model, we engineered a complete end-to-end data pipeline. Data ingestion, we developed a custom multi-threaded Python scraper to bypass both detection and collect data efficiently. Database management, we use a PostgreSQL relational schema to manage metadata like label IDs and URLs for fast retrieval. Image pipeline, every image is dynamically processed via Cloud Binary CDN, where it's resized to 224 by 224 and normalized for our AI model. Infrastructure, we use GitHub for version control and manage our .h5 and .keras model checkpoints through integrated storage. This modular approach ensures our system is not just accurate but scalable and production ready. Building on that architecture, we focus on our data ingestion layer. Instead of a single script, we engineered a modular framework to ensure high-quality data. As you can see on the slide, we developed specialized Python modules for each stage. fcscraping.py and orgscraping.py handle different website structures. cfg download images.py manages secure file downloads and naming. Comprehensive scraper.py orchestrates the entire flow from scraping to database management. By separating these tasks, we successfully organized over 6,000 images, creating the strong foundation our deep learning model requires. Continuing with our pipeline, let's look at the critical module, cfc download images.py. The script automates the acquisition of raw images and manages their transfer to our Cloud Binary CDN. Key functionalities include byte stream processing. For a major performance boost, we use io.bytes.io to process images directly in memory, avoiding slow disk operations. Cloud Binary integration, images are automatically uploaded to the cloud, giving us optimized URLs for our AI model. Error resilience, we implemented robust try-except blocks to skip broken URLs and handle timeouts, ensuring the pipeline never crashes during long runs. By using the Cloud Binary SDK and Pillow, this module effectively bridges our raw data sources with our cloud-based AI environment. Now let's discuss the entry point of our entire pipeline, the cfc scraping.py module. This script is responsible for crawling targeted websites and extracting critical origami metadata. To ensure this system is both efficient and resilient, we implemented several key elements. Beautiful soup, we use BS4 to parse complex HTML structures, pinpointing model names and difficulty levels with high precision. Batch inserts, using psychopg2.extras, we send thousands of rows to our PostgreSQL database in a single transaction, significantly optimizing storage speed. Anti-bot measures, to avoid being flagged, we integrated randomized request patterns and dynamic sleep intervals to mimic human behavior. Data integrity, we use regular expressions and your lib.parse to clean raw text and ensure all links are converted into absolute URLs before storage. In short, this is a sophisticated tool that ensures our database is populated with clean, structured, and reliable information. While the previous modules handled specific tasks, comprehensive scraper.pv is the brain of our data acquisition system. Its primary role is to coordinate the efficient collection, processing, and storage of thousands of high-quality origami images. To achieve industrial-grade performance, we integrated several core libraries and tools. Thread pool executor, multi-threading. This is our most significant performance feature. By implementing multi-threading, we are able to speed up the simultaneous downloading and uploading process by up to 10 times compared to a standard sequential script. Beautiful soup and requests. These serve as our web scraping engine, allowing us to navigate and extract data from even the most complex and nested HTML structures. Cloudinary integration. To keep our local environment light and the application scalable, we host all image assets externally. This significantly reduces local server load and improves asset delivery speed. PsychoPG2 and UUID. For every single image we collect, we generate a unique identifier using the UUID library. This ensures total database integrity and prevents any duplicate entries when syncing with our PostgreSQL metadata management system. In summary, this script ensures that our AI model has a constant, clean, and massive stream of data to learn from, handled with maximum efficiency. Many modern platforms hide their data within complex structures. This is where orgscraping.py comes in, turning messy web data into a structured knowledge base. To handle these technical challenges, we focused on 4 areas: deep URL deconstruction. Using our lib.parse, we deconstruct complex URLs to extract IDs and clean source paths with high precision. Decoding hidden data. We use JSON and HTML libraries to decode metadata hidden inside query parameters and embedded scripts. CLI flexibility. By implementing argparse, we can run different parts of the pipeline, like scraping versus downloading, independently. Data freshness. Every entry is timestamped using datetime, allowing us to track synchronization between PostgreSQL and Cloudinary. This module ensures that no matter how hidden the data is, our system captures it accurately. While modularity is key, we also needed a way to orchestrate everything smoothly. This is where fullscriptdirect.py comes into play. Think of this as the single execution trigger that runs our entire pipeline in a strict logical sequence. This script moves us beyond simple scripting into true data orchestration, seamless automation. With a single trigger, the system handles link discovery, metadata parsing, and cloud integration without any manual intervention. Modular design. Because the system is unified, we have the flexibility to swap core components, like changing our database or cloud provider, without causing any system downtime. Data consistency. It ensures real-time synchronization between our local metadata and remote media assets, ensuring that every image in our cloud has a corresponding accurate entry in our database. Now let's look at our live schema. Our system isn't just a list of names, it's a comprehensive ecosystem of 13 interconnected tables. The models table at the center, we capture technical metadata like difficulty, paper shape, and Boolean flags for glue or cutting. This allows our AI to categorize models with high granularity. The images table, this is our bridge to the cloud. We store the Cloudinary URL and a unique image hash for every asset. This ensures zero duplicates and maintains the high quality of our training data. Granular queries. This relational design allows us to instantly filter complex models by specific artists or paper types, making our training pipeline incredibly effective. Beyond identification, our system preserves the intellectual property and history of origami. This is why the creators and publications layer is so essential. Creators and aliases. We don't just store names, we track biographies and historical context. Our aliases table uses name normalization to link different international names to a single unique identity. The instructional engine, through the publications and model publications tables, we track books, magazines, and ISBN numbers. The bridge. Most importantly, this layer tells the user exactly which page of which book contains the folding instructions for the model they just scanned. By integrating this metadata, we have transformed a simple recognition tool into a comprehensive digital archive. To build a robust AI, we need a vast dataset. We developed custom scrapers to ingest data from leading authorities like Origami Club and the Origami Resource Center. Multi-threaded scraping, our CFC diagrams and org models tables are the result of high-speed scraping, capturing everything from original URLs to specific difficulty levels. Community Hub. Beyond models, we also collect metadata on events and educational resources, making our database a real-time hub for the origami community. Cloud resilience. Every external image is automatically uploaded to Cloud Inary. By storing the Cloud Inary URL, we ensure our AI model has permanent access to training data, even if the source website goes offline. This automated process provided the high volume fuel needed for our neural networks training phase. To conclude our architecture, let's look at the crawl management layer, the control tower of our pipeline. Since web scraping is never 100% stable, we built this robust tracking system, the crawl jobs table. This acts as our high-level monitor, tracking every execution, processing time, and item count to measure our scraper's efficiency. Granular debugging. In the crawl job items table, we store raw data in JSONB format. If a website structure changes, we can pinpoint exactly what went wrong without losing data. Error handling. By logging specific error messages, we can identify broken URLs or IP blocks immediately, ensuring the system remains resilient. In summary, these 13 interconnected tables bridge the gap between raw data and automated management, ensuring our AI is supported by a reliable and maintainable pipeline. Now let's focus on our cloud strategy. Storing over 8,700 high-resolution images locally is not efficient, so we integrated Cloud Inary as our primary media solution. Storage independence. By offloading assets to the cloud, our backend remains lightweight and independent of local hardware. Direct URL mapping. Instead of large binary files, we store optimized URLs in PostgreSQL. The AI fetches images directly from the Cloud Inary CDN, significantly reducing latency. Automated pipeline. Our CFC download images.py module handles the transfer, retrieving a unique public ID and syncing it with our database automatically. Scale ready. We are currently managing nearly 9,000 assets. This architecture allows us to scale to hundreds of thousands of images without worrying about disk space. Once our data ingestion pipeline was complete, we moved from collection to validation. Having a large volume of data is meaningless if the data is biased or poor in quality. This section covers the statistical insights we gathered to ensure our dataset was ready for the training phase. By using specialized scripts like modelstats.pva, we performed a deep dive into our data to identify class imbalances and geometric correlations. Our goal was simple: to move beyond raw images and create a high-integrity dataset that allows our AI to generalize effectively across different origami styles. To optimize our AI, we moved from a raw collection to deep analysis using advanced charts.pva. The tech stack. We used pandas and numpy for complex matrix operations to prepare our features. Visual insights. With Saborn and Matplotlib, we detected class imbalances. For example, identifying overrepresented models allowed us to use data augmentation to balance the training. Live integration. A direct bridge to our PostgreSQL database ensures our analysis always reflects the most current production data. This guarantees our model starts with the highest quality foundation. Origami is a creator-driven art, so we developed creatorsanalysis.pva to understand our data sources. Top contributors. Using bar charts, we identified the most frequent designers, ensuring our AI learns from world-renowned origami masters. Complexity distribution. We analyzed simple versus complex specializations to ensure a diverse range of folding philosophies. Global diversity. By tracking metadata from creators worldwide, we built a versatile model that recognizes styles from any school of design. This diversity makes our AI robust and ready for real-world testing. This slide represents the core transition from data collection to academic insight. The model stats.py module is where our raw scraped data evolves into the statistical foundations of our report. Database connectivity using PsychoPZ2, we established a secure and direct tunnel to our PostgreSQL database. This allowed us to fetch live metrics and metadata in real time. High-speed ingestion to avoid system bottlenecks. I implemented thread pool executor. This multi-threading engine allowed us to ingest and process thousands of image records simultaneously, significantly speeding up the pipeline. Advanced analytics. By leveraging pandas, we performed complex joins between our origami models and their corresponding complexity scores. This gave us a clear picture of our data quality. Visualization. Finally, we used Seaborn and Matplotlib to generate the distribution plots and correlation matrices that you see throughout this project. It's not just about numbers, it's about visualizing the health and balance of our dataset before it ever reaches the AI model. To conclude our analysis, let's look at the advanced summary of our global database. This overview highlights our dataset's diversity and technical precision. Difficulty distribution. We have a strong foundation of over 20,000 simple models, but we also include intermediate and super complex pieces to ensure high-level AI recognition. Pure techniques. A key highlight is that 95.6% of our models use no cuts or glue. This ensures our AI focuses on authentic proper folding art, proper shapes, while the square is our gold standard with 33,000 entries. We also support rectangles and polygons, making our model versatile across all initial geometries. This granularity is what makes our training pipeline so effective. To ensure our AI's reliability, we performed an extensive statistical deep dive into our dataset. This slide visualizes our data integrity difficulty distribution. We've built a massive foundation of simple models, allowing the neural network to master basic geometries before moving to complex structures. Heatmap insights over difficulty versus piece count. Heatmap is a critical diagnostic tool. It helps us identify and remove outliers, ensuring 100% accurate data labels. Technique validation. With over 42,000 pure origami models using no cuts or glue, we've eliminated the noise of mixed media crafts. This rigorous validation ensures our training data is balanced, clean, and architecturally sound. To optimize our AI, we moved from raw collection to deep analysis using advanced charts.py. The tech stack, we leveraged pandas and NumPy for complex matrix operations to prepare our features for the neural network. Visual insights using Seaborn and Matplotlib, we detected class imbalances. For example, identifying overrepresented models allowed us to use data augmentation to balance the training. Live integration. A direct bridge to our PostgreSQL database ensures our analysis always reflects the most current production data. This ensures our model is built on a balanced and accurate foundation. To ensure the academic and artistic quality of our dataset, we analyze the origin of our models. This chart highlights the top 30 most productive creators in our database. High volume sources. As you can see, major entities like the Origami Resource Center and traditional designs provide the largest portion of our data with nearly 4,000 models each. This gives our AI a solid foundation in classic folding techniques. Data credibility. This analysis isn't just about names, it's about source validation. Knowing exactly who designed its model allows us to cross-reference styles and complexities, which is vital for building an AI that can distinguish between a simple bird and a complex geometric modular structure. Now let's move to the brain of our project, the AI and computer vision framework. To turn our dataset into a functional assistant, we chose a highly sophisticated architecture. Model selection, we are using MobileNetV2, a state-of-the-art CNN. I chose this specifically because it's optimized for mobile and edge computing, perfect for a portable origami assistant. Efficiency. The framework reduces parameters while maintaining high-dimensional learning. It's lightweight yet powerful enough to recognize complex folds. The trade-off, our main goal, is the best balance between accuracy and computational cost measured in flops. On the right, you can see our AI directory. TrainModel.py handles the learning phase, while PredictImage.py serves as the real-time engine that identifies the origami. To power our neural network, I developed the datagenerator.py module. This acts as the essential bridge between our PostgreSQL database and the TensorFlow environment. Memory efficiency. Instead of overloading the RAM, the system fetches metadata dynamically. This ensures our pipeline is scalable and free of bottlenecks. Standardized preprocessing. Using OpenCV, I implemented a layer that resizes and normalizes every raw image into a uniform tensor format compatible with MobileNetV2. Vectorization, we use pandas and NumPy to map categorical labels into numerical vectors, enabling the high-dimensional calculations needed for classification. In essence, this module automates the flow from raw scraped data to machine-ready intelligence. The final stage of our pipeline is the PredictImage.py module. This is the functional bridge between our trained.h5 model and the user's input. Optimization, we use 1D NN kernels to ensure fast execution even on standard local hardware. Real-time processing, every user image is passed through OpenCV to be normalized and reshaped for the MobileNetV2 input layer. Predictive logic, the model performs a forward pass to calculate the statistical likelihood of the origami species. Validation, we use Matplotlib to display the input alongside the AI's top prediction for immediate visual confirmation. The core of the learning phase is managed by TrainModel.py, where we integrate our custom generator with the deep learning architecture. Dynamic streaming, a key highlight is the origami data generator. Instead of loading the whole dataset, we stream images in batches. This ensures high RAM efficiency and prevents system crashes. Robust path management, using Python's os.path, I implemented a flexible structure. This allows the script to run on any machine, local or cloud, without manual adjustments. Automated logging, we've filtered the output to report only critical errors, allowing us to focus entirely on accuracy and loss metrics. This slide demonstrates the actual performance of our model during the training phase, with results visualized through the two key metrics of accuracy and loss over 50 epochs. As shown in the first chart, both training and validation accuracy exhibit a consistent upward trend. Notably, the validation accuracy reaches a peak of over 80%, which proves the model's ability to generalize effectively to new unseen origami images. Simultaneously, the second chart illustrates a smooth and synchronized decline in both training and validation loss. This convergence is a critical indicator that our MobileNetV2 architecture is learning features efficiently without encountering common issues like overfitting or gradient instability. Ultimately, these results validate that our entire end-to-end pipeline, from structured data generation in PostgreSQL to the final training execution, has successfully produced a robust and reliable origami recognition model. Finally, we bring everything together in the Hybrid Origami Assistant.py module. This is where AI meets classical computer vision and a modern UI. High concurrency, I implemented threading and multiprocessing. This allows the AI to run in the background while the UI remains fluid and responsive. Modern GUI, we chose custom Tkinter to create a sleek, user-friendly interface for non-technical users. Hybrid vision, by combining PIL and OpenCV, we perform real-time edge detection to give the AI the clearest possible view of the model. Robustness, professional error handling ensures the application stays stable during continuous real-world use. To elevate the user experience from simple recognition to a truly interactive educational tool, we've integrated a high-speed inference layer using the state-of-the-art Llama-3 70B model powered by Groq's language processing unit technology. By utilizing Groq's specialized hardware, we achieve inference speeds that are 10 to 50 times faster than standard GPUs, enabling near instantaneous feedback for the user. This integration is built on an OpenAI compatible API architecture, ensuring that the application provides real-time expert-level insights into the history, complexity, and specific folding tips of each recognized origami model. From a technical standpoint, the system is designed with professional standards for security and scalability, utilizing environment variables for secure API management within a cloud-based framework. Ultimately, this layer transforms the application into a hybrid assistant, one that doesn't just see the origami, but deeply understands and explains it, offering a seamless and interactive learning experience. To wrap up our technical journey, let's look at the Hybrid Origami Assistant in action. I've designed a user interface that is both powerful and simple to navigate. The process is straightforward. Attach, the user selects an image of their origami model. Query, they can also type a specific question or the model's name. Analyze, once they click Send, the AI performs the background inference without freezing the UI. Result, finally, the assistant provides the identified species and step-by-step instructions. This interface ensures that sophisticated AI technology is accessible to anyone with a single click. This project marks the successful journey from raw data scraping to the deployment of a fully functional hybrid origami assistant. By combining MobileNetV2 for visual recognition and Llama-3 for expert guidance, we've demonstrated how cutting-edge AI can breathe new life into ancient art forms. We have built a robust, scalable framework that bridges the gap between historical artistry and modern technology. This is a powerful proof of concept for preserving cultural crafts, making the intricate logic of origami accessible to everyone. This is just the beginning of what is possible when data science meets cultural heritage. To two individuals who were pivotal to this project: Professor Idan Tobis. As my data science professor, his guidance provided me with the academic foundation and technical rigor needed to execute this research. His teachings were essential in developing the machine learning strategies used in this assistant. A special thank you to Ilan Garibi, a world-renowned origami master and designer. I'm deeply grateful for his exceptional mentorship. His expert advice and creative insights were instrumental in refining the overall quality of this project. Finally, thank you all for your time and attention.